One of the most challenging tasks in automotive electrical diagnosing is locating short and open circuit problems. This video will show how easy it is to locate short and open circuit problems, trace and follow wires using the POWERPROBE Smart Electronic Circuit Tracer 2000. The ECT was made with the technician in mind. Technicians are faced with trying to locate short and open circuits every day. Normally, they would have to remove panels, molding, carpet, and anything else that might be in the way of wires or harnesses. The time it takes to remove and replace these parts usually take more time than the actual repair itself. Let the ECT solve some of these headaches for you. The POWERPROBE ECT consists of two main components: a transmitter, which sends an electronic signal down the path of the short or open circuit, and a receiver, which detects the signal and informs the technician of the condition and location of the suspect wire. Here we made up a little demonstration board with a simple circuit to illustrate its basic features. As you can see, we have a 12-volt automotive battery and a positive wire leading to a fuse socket. This will be the positive side of the demo board, then passing over a short, which we will use later, to a switch, then a light bulb, which will be our load, then back to ground, and the negative side of the battery. Here we installed a heavy cable that's connected to the negative side of the battery. This will simulate a short circuit for us. As you can see, the circuit is working quite well until a short happens. Determining a short circuit is usually done by discovering a blown fuse in the fuse block of the vehicle. As we see here, the POWERPROBE is indicating a blown fuse. We start by removing the blown fuse and choosing one of the 4 adapters found in the ECT set. Connect the fuse adapter to the twin terminal of the transmitter's gray lead. Connect the black lead of the transmitter to a good ground. Insert the adapter into the fuse socket. When the transmitter is first powered up, it goes through a series of internal tests so you can see that all its indicators and the audio tone works properly. It detects the condition of the circuit and sends a signal down the wire and transmits an electrical field along the circuit. As we can see, the transmitter is indicating a short circuit. We need to make an important point here. This short circuit indication does not always mean that the circuit is shorted. It can also mean that the transmitter is connected to a normally closed circuit. This means that it can also be a complete circuit leading back to ground through a load such as a light filament, relay winding, or a motor winding. In this case, however, we have the circuit shorted out. Now let's turn on the ECT receiver and see what happens. As you noticed, the receiver, similar to the transmitter, goes through a series of tests to show that the indicators and the audio tone are working properly. If the receiver doesn't receive a signal for 30 seconds, it will automatically power down. You can also turn it off manually by removing it away from the transmitting signal and pressing the power sensitivity button. The receiver will remain on as long as it's receiving a signal. When the receiver is first turned on, it will sense open or a complete circuit signal. It is also in its most sensitive state. This means it'll pick up the weakest open or complete circuit signals transmitting from the circuit. Notice that the closer you get to the wire, the more rapid the pulse. Also notice that whether the receiver is facing this way or that way, the short circuit direction indicator will always point in the direction of ground. At times, you may want to lock the receiver in the short circuit mode with maximum reception distance. This is done by holding the receiver as far away as you can from the wire without losing the signal, and then pressing the power sensitivity button. The ECT is now locked into the short circuit reception mode, which will pick up weak signals further away from the transmitting wire. This feature is used for grope localizing. Now once you have located the transmitting circuit, you will want to zero in a little closer by discriminating out the weak signals and concentrating on the strong signals. To do this, press the power sensitivity button again to unlock the short circuit reception mode and return back to the short open mode. You will know you are in the short open mode by the indicator pulsing while receiving a signal. Close in the distance between the transmitter and the circuit achieving maximum pulse rate and press the power sensitivity button once more. You are now locked into the short circuit mode again, but this time it picks up only the stronger signals closer to the wire. Follow the circuit along the length of the wire until you lose the signal, and at this point you can remove the panel, molding, or carpet to expose the wire. It is here where you will find the short circuit. The reason you lose the signal is because electricity travels down the path of least resistance back to the battery, and the chassis ground will absorb the signal until it recollects back at the battery terminal. Now that we have found the short, let's fix it for our next demonstration. Notice that you can still see the transmitter indicator showing short circuit on its display. But remember the beginning of this presentation, this can also mean a closed normal circuit conducting back to ground through a load, such as a light filament, motor winding, or a relay coil. Now let's remove the light and open the circuit. Suddenly the transmitter is sounding off and the open circuit indicator is now displayed. As I move the light in and out of its socket, the transmitter is switching from open to short circuit and alerting me to the fact that the circuit condition is changing in relation to my actions here. This feature of the transmitter is great for finding intermittent problems such as bad connections or broken wires. We are now going to remove the light bulb to the open circuit. The audio portion of the transmitter has done its job, so we don't need it at this time. So let's press the toggle tone button and turn the tone off. The open circuit signal is still being transmitted down the length of the wire, even though the tone is off. The transmitter is now sending an open circuit signal down the length of the wire and will transmit through plastic panels, molding, and carpet. But be aware that open circuit signals will not transmit through metal or wet material. Also note that when detecting open circuits, your hand and body can interfere with the reception if near to the pickup area of the receiver. Let me point out now that if the circuit was to go closed somehow, the audio portion of the transmitter will sound off, alerting us to the changed condition of the circuit. You can toggle the tone off again by pressing the toggle tone button. If it goes open again, the audio tone sounds off and you can toggle the tone off again. If you noticed, the transmitter puts out a lower tone when detecting a closed circuit and a higher tone when detecting an open circuit. Let's take the receiver now and turn it on. Remember, when you first turn on the receiver, it will look for a closed or open circuit and will pick up the weakest signals. Notice too that the closer the receiver is to the transmitting wire, the more rapid the pulse. Let's set the open mode distance. Now, let's follow the path of the wire, and right where we lose the signal, we will find the open. At this point, you can remove the obstruction covering the circuit. The ECT also detects open wires that could be broken inside the insulation. It will also lead to a connector that has been disconnected from the circuit. In automotive circuits, you will be dealing with circuits that run parallel throughout the vehicle. Most circuits are powered by the ignition or accessory switch. At times, it will be necessary to keep the switch turned off. This next portion of the video will deal with understanding how the ECT reacts to parallel circuits and how to diagnose them. Our demo board has been made up with 4 parallel circuits. On the right side, we supplied the board with 12 volts, and the left side is ground. These 4 light bulbs represent electrical components, and the switches will open or complete the circuit to them. We can disconnect each circuit by pulling their terminals from the positive or grounded side. Here we installed a heavy ground cable to simulate a short circuit. Let's start off by showing all circuits activated. Now here we will short out the circuit. The short just blew the fuse in the circuit. Let's remove it and choose the proper fuse adapter from the ECT kit. Now let's connect up the black lead of the ECT transmitter to this jumper wire we have connected to ground. Now the gray lead to the fuse adapter and insert it into the fuse socket. It powers up and indicates short circuit on the LED display. Let's turn on the receiver, bring it about 4 inches from the transmitting wire, and lock it into the short circuit mode at this distance. In the case of a dead short, almost all of the signal flows down the path of that short back to the battery. The other parallel closed circuits are deprived of signal strength. Watch what happens when we remove the short from the circuit. The signal is now distributed in this example equally among all 4 circuits. Observe the reception distance between them all. It's about 2 inches. Let me make a point here. We have the receiver locked into the first circuit at 7 inches away. The other parallel circuits are turned off. Now watch what happens when I turn on one of the switches of the other parallel circuits. See how we lost the signal? Let's bring the receiver down a little closer until we just pick up the signal. Look at the receiver now as I close another one of the switches. We lost even some more of the signal. Let's bring the receiver even lower just till we get the signal back. Now we will close the last switch. The point here is that all circuits and components that run parallel to the circuit you want to trace need to be turned off when tracing wires that are not short-circuited. Here is another necessary point to consider. If you are tracing a circuit that is not shorted and there are other circuits parallel to it, you need to isolate the circuit, as we will now illustrate. In this next example, we have parking lights, dash lights, tail lights, and running lights. In automotive applications, these circuits usually run parallel to each other. Let's say we want to just follow the tail light to determine its path in the vehicle. Isolate it by either disconnecting it or cutting it out of the circuit. Use the universal adapter to supply the signal exclusively to the taillight circuit. Clip the red lead to positive, and the green clip is the signal lead. Here again, the entire signal is being transmitted down the taillight circuit and giving us a strong signal. Here we see that the other circuits have no influence on the receiver now. Let's address parallel open circuits now. In this example, we will use the universal adapter. Connect the black lead of the transmitter to ground and the red lead of the universal adapter to battery positive. The green wire is our signal wire. Let's connect the signal wire to the open parallel circuits and see how they react. As we observe, the open signal is transmitting from all open circuits on the board. We need to isolate the circuit we really want to diagnose and inject the signal directly into it. Now observe that the other open circuits are no longer transmitting because our circuit is disconnected from them. If you have further technical questions, please give us a call and we will be happy to assist you.